Hello. In this video I want to present a derivation of the Euler-Lagrange equation, which I think is a bit easier to understand and more intuitive than the standard derivation presented when you first encountered that when you study physics. So the setup is that we have some variable x, which I will call here a position, because in physics we really want to know what is the position in phase space or what of a particle as a function of time. So we have this position x that depends on t, which is time. Of course, this setup applies to other settings in which, for example, here we don't have a time, but we can have, for example, a way to find the minimal distance between 2 points on a non-flat space, things like that. So we have this function that depends on position, the derivative of the position with respect to time, so the speed of the particle, and time. And we want to minimize the integral from a first time, ta, to a second time of this function as a function of x dot and t integrated over the time, and we want the minimum, which in fact what we want to find is what is the function x of t that minimizes this integral. And when you do these calculations with the function being what we call the Lagrangian in the classical mechanics, we get back to the equation of motions, which are equivalent to Newton's equations of motion. And this is called the principle of least action. But of course, this formulation, this problem applies to many other types of optimization problems. So how are we going to do that? Well, I think the most intuitive way of seeing that is that we can take this integral and change it to a Riemann sum. So the integral of f dt, and then we would just highlight what we want to do. We want to express this, and then to find the minimum, we will use the classic calculus optimization criteria that the derivative with respect to some variable is equal to 0. So the minimum of this, so this thing here in blue is equal to the summation over some index k of f of x at tk x dot at tk delta t, and k will go from, for example, from 0 to n minus 1 for n intervals, and we have delta t equals tb minus ta over n. And of course, I'm not writing it here, but we will assume that n is very large and delta t is very small, and in fact these things are equal in the limit of n becoming infinitely large. But I will not write the limit all the way because it's just a bit cumbersome. It will just take space on the blackboard and doesn't contribute too much. But we have to keep in mind that delta t is in fact small. Okay. Now, x at time tk, so these time tk's are tk equals to k delta t, simply. So now x at time tk, it's easy to see what it is, just the position, but what is the derivative of the position at time tk? Well, this one here, we can express as a function of x at different times, because the derivative is equal to x at time tk plus 1 minus x at times tk over delta t. So now we took this problem that had a dependency on the position and the speed, and we just made it into a problem that has a dependency only on the position, and we took this problem which looked for a continuous function, and we discretized it over many very small time intervals. And now the trick will be to optimize this. So we want to find the minimum of this. So the minimum will be obtained as in any problem using calculus of multiple, with the multivariable calculus, we need the derivative with respect to x of tk of this thing here equals 0 for all the tk's. Because here we see that x of tk is becoming a discrete variable. We have n-1 variables which correspond to the position at each time. So we have position at time 1, time 2, and so on and so on. So the next board, I will rewrite this, and I will change the notation a bit because it becomes really large and it just kind of obscures the fact that x at time tk will be simply written as xk. So on the next board, we'll continue the problem. Okay, so using the notation I had on at the end of the last board, we want to minimize this sum, which is the sum from k equals 0 to n-1 of this function evaluated at different k's, and the function depends on xk, and here the difference between hk plus 1 and xk divided by the time interval delta t and t. And of course we had this delta t here. And here tk. So to see what's happening here, I think it helps to rewrite the first few terms of this function here. So is this sum. So the sum is equal to f of x0, so x1 minus x0 over delta t, t0, delta t, plus the same thing, f of x1, the difference between x2 and x1 over delta t, and t1, plus, I will just write the first few terms and explain where this is useful. x2, x3 minus x2 over delta t, t2, delta t, plus, and so on and so on. So what we want to do is minimize the sum, and to minimize the sum, we need to have that the derivative of the sum here, I just had it as a blue square, the derivative of this big sum with respect to all the variable xk was 0. So the derivative of this sum with respect to x0 equals 0. The derivative of the sum with respect to x1 equals 0. And so on. So what I took is I took this very difficult problem of finding the minimum of an integral. So what I did is I took this problem of finding the minimum of an integral and I transformed it in a problem of finding the minimum of a multivariable function, which we know how to do from basic first year multivariable calculus that everyone in physics takes. So what we need to do is took the derivative of this function. This is the function we want to minimize. And this function depends on all the xk's. So x0, x1, x2, and so on and so on. And the function will be a minimum. So in fact, it would be a maximum, strictly speaking, but in physics, what we will find usually is the minimum. So this function which depends on all these variables, x0, x1, x2, and so on, we'll have a minimum when the derivative of the function, which is this whole sum with respect to x0 is 0, with respect to x1 is 0, and so on and so on. Now, I wrote this out in details for the first few terms because we see that, for example, if we take the derivative with respect to x1, well, these terms here, x2, x3 minus 2, and so on, and all the other terms which have on the largest indices, they don't depend on x1. So the derivative of this thing with respect to x1, for example, will go to 0. So we're left with two terms. Which terms depend on x1? Well, this term will depend on x1. Will depend on x1 in two respects. Will depend on x1 as depending directly on x1, and will depend on x1 as depending in the second variable as depending on x1 and x2. And here, it will depend on x1 because there is an x1 here in the second variable. So if we remember, the second variable was the variable corresponding to the speed, which we'll consider as being something that we can find independently from the position in these types of problems. We have to specify both the position and the speed of the particle to know its state, as usual in mechanics, because the equations of motion are second-order differential equations. So all the terms, for example, when we derive with respect to x1, will disappear except for two terms: the term with the x1 corresponding to the index we're looking at, and the preceding term. But this will be valid for x2, this will be valid for x3, and so on, for any xk. But this will be valid for all k's. So what we do when we take the derivative with a certain xk is we need to keep only two terms in our sum. We need to keep the term that corresponds to the position at time k, xk, and we also need to keep the term that corresponded to the previous position because it's needed in the second variable, the derivative. So this whole sum for each of these equations contains only two terms, and that's what I write on the next board. Okay, so we saw that for when we optimize, like we take the derivative with respect to a certain xk, we need to keep two terms. So this means that to minimize this function here, we need to have the derivative with respect to xk for all k's of f of xk plus 1 minus xk over delta t and tk delta t plus the derivative with respect to xk of the previous term, f of xk minus 1 xk minus xk minus 1 over delta t and tk equals 0. So now we had this function here, which depends on three variables. This was x, but let's call it a because it would make things much clearer. Let's call this one a and b. So if we have the original function, which depended on x, the derivative of x and t, we replace these variable x and this xk plus 1 xk and delta t by b. So we have a function of three variables, a, b, and p, and we take the partial derivative with respect to xk. So we use the chain rule. Maybe this is not clear. The way to see it is that if you have a function of a and b and b are function of z, then del f del z is equal to del f del a del z plus del f del b del B, del Z. So that's the standard chain rule that we use in multivariable calculus. Here it's the same. We have this thing here that has three entries, three variables, and these variables are dependent on the different xk's. And we will use some notation here. We'll use the fact that del F, del A will use a notation FA, which is one of the standard notations for partial derivatives, so that we don't get mixed up in all the x's and so on. So if we take this derivative, well, there will be two terms here. The first term will be the derivative with respect to A, so this will be, and A before was F was the function of A and B. It was, let's call it FA, and we'll figure it out later. FA, and the derivative of fxk with respect to xk is 1, so that cancels out, delta t. And then there will be another term here, plus fb. But now we have to be careful. The derivative of xk of b is minus xk over delta t. So that's times minus xk over delta t. And then there will be another term for this derivative, and here we would get the factor 1 over delta t. So this will be fb times 1 over delta t. Now I wrote it shorthand, but we have to be very careful at which point these things are evaluated. Here, this FA is in fact FA at xk plus 1 minus xk over delta t, tk. And this term here is fb at xk plus 1 minus xk and tk, and this one here is fb at xk minus 1 xk minus xk minus 1 tk. So what we notice here is that these two fb are evaluated at two consecutive points and they are divided by delta k. So what is that? Well, that's simply the derivative, because there's a minus sign in between these two. So this minus sign here, there's a minus here, and if we take these two things here, if we look carefully, we will see that they are basically the difference in fb between the point at xk and the point at xk minus 1, so at times tk and tk minus 1. And we divide by delta t, so that's in fact the derivative. And we divide by delta t, which in fact gives us the definition of a derivative. So if we rewrite this, we will see that this derivative is equal to, I will write that on the next board. So we add here the derivative with respect to xk of this thing here is equal to then fa, and we have f is equal to f of a, b, and t is equal to fa minus, we had this difference, this derivative that we had of FB, which was equal to 0. Now, I kept A and B so as not to introduce any confusion, because it can be a bit confusing. Just to make things clearer, so far we only did multivariable calculus, very standard things for functions of two variables, which are themselves functions of order variables. And what we need to do here to obtain the Euler-Lagrange equation is to get back to our original notation, in which we had that A was in fact a position, B was a speed. So this is equivalent to the fact that del f del x minus the derivative with respect to time of del f del x dot is equals to 0, which are the standard Euler-Lagrange equations. And that's it for today.